In this week's lab, we'll be investigating atomic spectra. The way that we'll be doing this is by exciting a gas of atoms. Usually this is done by shooting electrons through the gas using a high voltage. The electrons strike the gas atoms, exciting the electrons in the gas atoms to higher energy levels. Then when the electrons in those atoms drop back down, they emit light. And because there are discrete differences in energy levels, the light that gets emitted occurs only at certain specific wavelengths. And we'll be taking a look at those wavelengths to infer the electronic structure of the atoms. We will be paying particular attention to hydrogen, because hydrogen, having only one electron, has the simplest atomic spectra. In fact, the atomic spectra of hydrogen follows this relationship here, where 1 over the wavelength is equal to the Rydberg constant times 1 over n. N is the starting, or n is the ending up energy level, so that's where the electron goes to, and 1 over m. M is the starting energy level. So we'll be looking at the Balmer series because those are the wavelengths that occur in the visible part of the spectrum. All the other wavelengths are either in the infrared or the ultraviolet. So in the Balmer series, we end up with the electrons falling down to n equals 2. And they start out at m equals 3, 4, 5, 6, and so on. And so if we make a plot then of 1 over lambda versus 1 over m squared, then we can use the slope to infer the Rydberg constant. So this is the first setup for part 1 of phase 1 of our atomic spectra lab. So this wooden thing here is an open spectrometer. So as you can see, we have at one end a diffraction grating. So there's a washer here with a diffraction grating magnetically attached to it. And so that diffraction grating is going to split up the light coming through it into its constituent colors. And when we look through the diffraction grating, we'll see the light coming through this slit, broken up into its constituent colors and projected on either side of the slit. And so if we remember last time when we looked at a diffraction grating, we could measure the angle of where the first order maxima appear, and that will tell us something about the wavelength of the light. And we're going to do the same thing here. So when the light shines through the slit, we can look through the diffraction grating and see where the constituent colors appear. So the first thing we're going to look at is hydrogen. We have a hydrogen bulb in our high voltage power supply, and so let's turn that on and see what we see. So as you can see, the diffraction grating right now is looking at hydrogen, which gives off kind of a pinky purple light, and when that light shines through the slit, we can look at the slit through our diffraction grating, and the constituent colors appear on either side. So we need to measure the locations of those colors, the red and the light blue, the kind of the cyan, and then the dark blue. And those are the colors that make up the hydrogen emission light, at least in the visible part of the spectrum. So we're going to measure their positions, find their angles with respect to the center slit here, and that will tell us the wavelengths of those particular colors of light. So here we have the setup for phase 1 part 2, where we're now going to take the spectra of the hydrogen light with a spectrometer, an electronic spectrometer this time. So we see that we have pointed at the hydrogen light a fiber optic, and that fiber optic cable is going into a spectrometer, and the spectrometer has inside it a reflection diffraction grating and breaks the light up once again into its constituent parts. And this is attached to a computer, And here on the screen, you can see the spectrum that we're getting. So the different lines that we're getting from the hydrogen. And you can see this big line right here. This is the red that we were seeing before. This is the cyan line, and this is the blue. Then over here we have some ultraviolet peaks that you can see just. So what we're going to do is measure the location of these peaks in nanometers, and then also the widths, so we get some idea of the uncertainty in those spectral lines. We'll also be using the Project STAR spectrometer to take a look at the emission lines from various gases. So as you can see here, we're set up to look at hydrogen, and the Project STAR spectrometer works much like the open spectrometer from phase 1 part 1. So there's a slit at one end, so this right here's a slit, and that is pointed at the light source, and then you look through a diffraction grating here at the other end, and the lines are projected along this side here, along this arc, and that arc is labeled with the wavelengths at various angles, so you can read off the wavelengths directly from the back of the spectrometer. And here we have the helium in the discharge tube, and as you can see, the helium gives off primarily kind of a peachy color. The helium spectrum is a lot more complicated with many more lines than hydrogen. Here we're looking at the helium discharge tube with this Project STAR spectrometer. And next we have neon, which is unsurprisingly a neon in color. The spectrum of neon, as you can see, has a lot of lines in the orange and red part of the spectrum. And here we're looking at neon with the Project STAR spectrometer. The last kind of lamp that we'll take a spectrum of is the Mercury lamp. So Mercury also has a slightly more complicated spectrum than hydrogen. And here we have the Project STAR spectrometer set up to look at the spectrum of the Mercury lamp.